In this video, we are going to come up with a differential equation to model the mass on a spring, okay? So, suppose we have some spring just hanging there. And now suppose we connect a mass to that spring so that the spring would stretch like this. So now we have a mass on there. So that's why the string is stretched. And we're going to call this distance S naught. Okay? Now, if the mass is just sitting there and nothing is touching it or acting on it, then it's going to be in equilibrium, meaning it's not going to be in motion. Okay, so this is going to be our equilibrium position, y equals 0. So here, y of t is going to be the position of the mass. And we're setting this equilibrium to be y equals 0. So at this place here, spot at equilibrium, the force of gravity is equal to the restoring force. Okay, the restoring force we can get from Hooke's law. And Hooke's law just says that the restoring force is equal, the force that's pulling this mass upwards, right, is equal to some constant k times the distance that the spring is being stretched. And here the spring is being stretched a distance of S naught. Okay, so this here is being S naught. Now, if we want the mass to be in motion, we're going to stretch the spring, or compress it. So say we stretched it like this, pulled the mass downwards, and we're going to call that distance here y of t. So y of t here is the distance from equilibrium that this mass is stretched, okay, on the spring. And this distance here will be positive, say, if it's over here, or we could compress it. So say we compressed it like this. We could call that distance y of t as well. And up there, y of t would be negative. Oh, sorry, this would be y of t. The distance from equilibrium. Okay, so just remember that when I say y of t's position, it's the distance from the equilibrium position. Okay. Now, what are the different forces that could be acting on this mass right here? Okay, so we're going to have the sum of the forces acting on that spring is equal to mass times acceleration. Remember, the acceleration is the second derivative of position. And so some possible forces we could have are, we have the force of gravity plus the restoring force plus any frictional forces such as air resistance or some kind of damping force. I'm just going to refer to it as a frictional force right now. Or we could have an external force. Okay, the sum of the forces acting on the object is equal to the mass times the acceleration. Okay, so the gravity is mg. Then we have the restoring force, which is opposing gravity. So here we have a minus k, and we get the restoring force from Hooke's law, which says that the restoring force is proportional to the distance that the spring is stretched. So here we're looking at this position right here. So what's the distance that is being stretched there from this spot right here? Well, it's being stretched a distance S naught plus y. So here we have S naught plus y. Okay, so there's the restoring force plus any frictional forces. Now the frictional forces could take different forms, but here we're going to assume that the frictional force is proportional to the velocity. Okay? So the frictional force here would oppose the motion. So we're going to put a minus sign. So it could be like some constant c times the velocity v, but v is y prime. So we're going to write minus cy prime for the frictional force. Then we have the external force. Here we're going to assume the external force is just some function of time. which we don't know right now. We'll just specify it as f of t. And then equals mass times acceleration, okay? Now, if we write that over again, notice that from right here, we have mg is equal to ks naught. So here, this mg will cancel with this k minus ks naught because mg is equal to ks naught. And so what we're left with is the following differential equation. We have, just coming from this part right here, we have my double prime plus cy prime minus ky, or plus ky, because we're bringing it all to the side of my double prime. So plus ky equals the external force. Okay, so this is our differential equation that we got for the motion of the object mass on the spring. We have mass here, y double prime plus cy prime plus ky equals external force. Okay, so this is a differential equation for y of t, and we'd want to solve this equation for y of t, the position. Okay, so this is a second order equation because the highest derivative appearing is y double prime. It's second order. It's also linear. It doesn't have to be linear. It could be non-linear, which we'll talk about later maybe. But for this course, we're going to be looking at this equations of this form a lot that are linear and second order. And there's also constant coefficients. So what I mean by that, constant coefficients, is that the coefficients in front of y double prime, y prime, and y are all constants. So this is a very popular differential equation that shows up in all types of different places in physics and mechanical systems, such as this one here. And we're going to learn, spending a lot of time in this course learning how to solve those.